Welcome to this explainer. You know, whether it's that tight plastic packaging keeping your coffee beans perfectly fresh or the thermos keeping your morning water piping hot, we interact with vacuums literally every single day. But what exactly is a vacuum degree? Today, we're going to break down the invisible science behind this everyday term and see exactly how it powers our most advanced modern technologies. Okay, let's dive right into this. Is a vacuum truly empty? Because most of us picture a complete void, right? Just absolute nothingness where not a single speck of matter exists. Well, according to physics, that's a total myth. Achieving an absolute zero pressure is practically impossible. Let's look at section 1. Vacuum is not empty. The myth of absolute zero. So here's the actual definition. A vacuum is really just a state within a specific space where the gas pressure is lower than the standard atmospheric pressure outside, which sits at roughly 101,325 pascals. So vacuum degree is basically just a scientific metric for measuring the thinness of that gas. The closer the pressure gets to zero, the fewer gas molecules are bouncing around in that space, and boom, the higher your vacuum degree. It's that simple. Moving on to section 2. Measurement standards, absolute versus relative. So the crucial point is that you've got to know your reference framework, and industry uses two main ones. Absolute pressure is the scientific standard. It starts at a true absolute zero and ranges up to 101.325 kilopascals. It tells you exactly how much pressure is actually there. Relative gauge pressure, on the other hand, starts at whatever your local room's atmospheric pressure is. And because it measures how much lower the pressure is compared to your surroundings, high vacuum readings in this system actually look like negative numbers. Pretty wild, right? Now, depending on where you are in the world or what industry you're in, you'll see a few different units slapped on equipment labels. Pascal, or PA, is the international scientific standard. Then you have torr, which is a historical unit named after an Italian physicist, sitting right around 133 pascals. Millibar is incredibly common in European labs and meteorology, and that cleanly equals exactly 100 pascals. And finally, PSI, or pounds per square inch, which is a really frequent sight in North American pneumatic and hydraulic systems. Which brings us to section 3, vacuum levels, the 4 tiers. Let's move to the 4 tiers and see how this builds, because not all vacuums are created equal. We rigidly classify them based on pressure. Low vacuum is anything under 100,000 pascals. This handles your everyday stuff, like food packaging and industrial suction cups. Medium vacuum, dropping under 100 pascals, is the active zone for industrial drying and chemical distillation. Then things get extreme. High vacuum, under 0.1 pascals, is strictly required for manufacturing semiconductors and optical coatings. And finally, ultra-high vacuum, plunging way below 0.0001 pascals, is the absolute extreme environment needed for stuff like space simulation and high-energy particle physics. Let's dive deeper in section 4, mean free path, distance between crashes. Now, what's really interesting about this slide is the concept of the mean free path. Think of this as the incredible distance a single gas molecule can fly before it inevitably crashes into another molecule. Down here in our normal, everyday atmospheric pressure, it can only travel about 68 nanometers before collision, basically nowhere. But in a high vacuum, that single molecule can fly for several kilometers without hitting a single thing. And this is exactly why an electron microscope absolutely needs a high vacuum to operate. If it didn't, the electron beam would just smash into air molecules and scatter everywhere instead of capturing a precise image. And finally, section 5, industry applications, purity and precision. And this brilliantly illustrates a massive point. When you're chasing extreme vacuum levels, the biggest challenge isn't just pumping the air out. It's controlling pollution. See, traditional pumps use lubricating oil, which can easily vaporize and flow backwards, entirely contaminating your pristine clean chamber. That's exactly why equipment like these GOL oil-free scroll vacuum pumps are a total game changer. Creating a completely dry, oil-free vacuum environment is the absolute baseline requirement for modern semiconductor and precision medical manufacturing. So the next time you use your smartphone, just ask yourself, what level of extreme purity and high vacuum did the tiny microchip right inside your hand have to go through just to exist? Because understanding vacuum degree doesn't just teach us about empty space. It reveals the invisible, ultra-clean foundation of the modern precision technology we literally rely on every single day. Thanks for joining me on this explainer, and definitely keep questioning the amazing science hidden right in front of you.